right, let's see if I get the video going too. All right, perfect. And I can see myself, so hopefully you can see me as well. How are you? Looks like it's just going to be us today. I'm sure maybe a couple people will straggle in late, but being a long weekend, I'm not expecting anybody. Thank you for showing up. I really appreciate it. I'm good. It's still sunny. I have my window open, and it's nice to still see the sun. I don't think that'll last very long. It's already getting quite chilly, so yeah, we'll have to see. I'm hoping that you're good. You said that you're good. I hope you stay good. I know that you guys are just drowning in midterms right now, so I feel quite bad for you guys. Before we begin, can you see my screen? I started sharing it earlier, but I'm not sure if it popped up. All right, wonderful. So let's just start into it. I know that you're probably excited for the long weekend, as am I, so we'll get through this nice and quick. The nice thing is, from the 2 in-person seminars, this one's only about 40 minutes. It's quite quick because the assignment this week is pretty simple. You will see that it's not a big deal at all. There's only 1 or 2 questions that can be a little bit tricky, but we're going to go over them, so hopefully there's no problems, all right? So if you have any questions, just throw that in the chat. I say that every assignment, but have the assignments been hard? What do you think? I'm generally curious. To me, they seem easy, but of course, I'm biased. So what do you think? Are they pretty tough? Okay. Struggle with time for the last one? Okay. For the assignment or the midterm? Because, yeah, the midterm was definitely, it can be a time crunch. Okay, assignment? Okay. Well, hopefully this one goes better. The nice thing of it just being you and I is if you have any questions, we can slow right down and go through everything, okay? So don't be shy. I'm here to help. Anything you need, just let me know, okay? We'll jump into it. Let's see if I get this clicker working. Alrighty. Alright, perfect. Okay, now the clicker works. Alright. So question 1 is all about uniaxial strain. So basically just strain in one direction. If I were to pull steel or crush concrete, as we know, we're only pulling in one direction. And that's all of question 1. Question 1 says a rod with unit length is subjected to uniaxial tension. Determine the instantaneous length of the rod under the following conditions. And as we can see in A, B, and C, they give us 3 different types of strain. Now the strain itself is always the same, but the type of strain is different. As we mentioned in the lecture, we have 3 ways of measuring uniaxial strain. We have engineering strain, true strain, and the green strain. And what this question is asking for is the instantaneous length. Now, it sounds a little bit confusing, but the instantaneous length is basically the deformed length. Okay, that's what we're after. What is the current length of the rod after I start to strain it? The key here is that we are given the original length. It doesn't explicitly say 1 meter, 2 meters, anything like that. But in the question it says the rod has a unit length. So its original length can be assumed to just be 1. Okay, that's kind of the only real trick. So for A, B, and C, all we're going to do is to determine that deformed length. Part D says comment on the difference in the deformed length in the 3 scenarios. So as you'll see, A, B, and C will give you different values for the current length of the rod. And part D, just comment on them. I'm not expecting anything too in-depth or anything. An example would be, let's say my engineering strain resulted in a larger deformation than the green. Something like that. Again, nothing too scientific. And then finally, E says, is there a stretch ratio where all 3 strains are the exact same? So we're going to go into the formulas and try and figure out, is there a scenario where this holds true? The best way to do that is just to look at each strain measure. So for the engineering strain, it's going to be lambda minus 1. For the true strain, it's going to be the natural logarithm of lambda. And then for the green strain, it's going to be 1/2 lambda squared minus 1. So if we look here, it's actually a simple question because in all 3 of these formulas, we're given the strain and our only unknown on the right-hand side is lambda. So all we need to do is solve for lambda using these 3 different formulas. The only trick that you have to be aware of in exams, because as we're going to see it's not going to apply here, is that lambda is our stretch ratio. It's not our deformed length, okay? The question's asking for the deformed length, not the stretch ratio. So what we would do is we would find lambda, and now that we found lambda, we can find its current or deformed length, because lambda is simply going to be the current length divided by the original length. Now in this question it's nice because since our original length was 1, it said it's a unit, our stretch ratio lambda is actually just going to be the same as the deformed length. So all you guys need to do in this question, figure out lambda and then figure out the deformed length, but since it's a unit length, they're going to be the exact same. So how does that sit with you? Is that pretty good? It's not too bad. All we have to do is find lambda, and that's basically going to be our answer for A, B, and C. How's that? I'm hoping it's nice and simple. Good? Perfect. So then part D, all I want you to do is take your results and comment on the difference. And then finally, the last part that says, is there a stretch ratio lambda where all three of these strains are going to be the exact same? So what do you think? Is there going to be a lambda where all three equations predict the exact same thing? I'm curious to see what you think. No, it actually is yes. And there's only one particular time it does that. I would have thought no the first time too, so I don't blame you. But that is this. All three of these formulas measure strain. Now, if I take an object, let's say it's my clicker here, and I don't strain it at all, so its original length is equal to the deformed length, okay? The two lengths are the same. What would my lambda be if I don't stretch this at all? My original length is equal to my current length, 1. And if I substitute 1 into every single one of these formulas, I'm going to get 0 strain. So that's the only time where it's the same through all these measures. And it makes sense because all three of these formulas measure strain. And if I take an object and I'm not straining it at all, well then all three of these formulas have to predict 0 strain. So that's going to be the one and only case. It's a little bit tricky, but it kind of makes sense. If you have a formula where I'm not straining something, but my formula predicts strain, that's not a very good formula. So that's why we tend to tend to stay away from it. So yeah, that's going to be the one and only case. So that's going to be question 1. Any questions or concerns with question number 1? Or are you feeling pretty confident? No, looks good. Perfect. So let's go to question 2. Question 2 has the trickiest question in the entire assignment, but after that, it's pretty simple. So question 2 says a cube undergoes a deformation such that the infinitesimal strain is described by, and as we can see, we have a second order tensor or a 3x3 matrix. Now, whenever you see the word infinitesimal strain, it's the exact same as saying small strain. So my small strain tensor, that's the same as my infinitesimal strain tensor. It's just a different word for it. And from this strain tensor, it wants us to determine 4 different things. The first one is the principal strains and their directions. The second one is the longitudinal strain along the direction of the vector dx, which is 1, 1, 1. The approximate change in angle between the vectors dx and dy, which is -1, 1, -1. And then finally, the coordinate transformation matrix Q that transforms our small strain tensor into a diagonal tensor or a diagonal matrix. So before we get into B and C, because those are going to be the tricky ones, let's look at A and B. They both have to do with principal strains. Now, my question for you is, what exactly are principal strains? Principal strains, principal stresses, they're all related to something very important that we talked about lots in our linear algebra. Do you remember what it is? No, that's fine. This is why it's nice to know. So whenever you see the word principal in this course, no matter if it's strain, stress, anything else, it always means eigenvalues and eigenvectors. Always. So for part A, where it's asking for the principal strains, that's a fancy way of saying it wants the eigenvalues of the strain tensor. That's it. You have a matrix here, 3 by 3, So if you were to throw it into Mathematica and then find the eigenvalues, those will be your three principal strains. Now, the direction of the principal strains, that's going to be our eigenvectors. So part A is all about eigenvalues and eigenvectors. That's it. If we look at part D, where it wants to transform our matrix here into a diagonal matrix, well, we said that that's done by taking our coordinate transformation matrix Q and making it so that the rows of Q are our eigenvectors. That's it. So once we find the eigenvalues and eigenvectors, we have A all done and we have D all done. The only real tricks are going to come into part B and part C, and we're going to talk about it. So let's go through nice and slow. So first of all, principal strains and directions. Again, whenever you see principal, you're going to see a lot with stress too, not just strain. It always means that we're trying to find the eigenvalues, always. And the direction of these principal stresses or principal strains, those are going to be our eigenvectors. So again, every time you see principal, eigenvalues, always. How do we do that? Well, we talked about it in all the other seminars, so I'm just going to go real quick. We're basically solving the equation, the determinant of, in this case, epsilon minus lambda I is equal to 0. And this is if you want to do it by hand. Chances are you're not going to do it by hand. So what we do is we just go into Mathematica and go eigenvalues. It'll give us our three values. Those will be our principal strains. Now for the eigenvectors, again, the same thing. We're just going to go to Mathematica, type in eigenvectors, and then we have our three eigenvectors. It's nice and easy. Now where this becomes a little bit more tricky is going to be in part B. So part B says, okay, I gave you my strain tensor. It's a 3x3 matrix. And it wants the strain in a very specific direction, in the direction of vector dx. So keep in mind that dx right here, it's a vector. Now, if we look back to our theory in our lecture notes, we have this formula. And this formula is for finding strains in any direction. The only thing that we need is going to be our small strain tensor, which we're given at the beginning of the question. And we need the vector, which defines the direction we want our strain in. In this case, it's dx, which we were given as 1, 1, 1. So all we have to do is basically just plug everything into this equation, and we will get our strain. Now, the equation itself, it looks pretty gross, but if we go through, it's actually not too bad. As we can see, we have that dx appearing 3 times. Now, the only trick with dx is when I see dx personally, I'm always thinking a derivative or an integral, something like that, some sort of differential. In this case, it's not. Dx is just our vector that we want the strain along. In the question, we said dx is 1, 1, 1. So in all 3 of these cases in this formula, that would be our vector 1, 1, 1. That's it. This part here is basically our small strain tensor, which is a matrix, multiplied by a vector. So my question for you really quick, if I were to take a matrix and multiply it by a vector, what's that going to result in? What do you think? Take a matrix, multiply it by a vector. A vector, exactly. See, you got this. So after we take our small strain matrix and multiply it by dx, we're going to get some vector. And that's great because then we're going to take that vector and we're going to dot it with dx. So my question is after I dot it, what's going to be on my numerator there? What do you think? A scalar, vector, what do you think? Scalar, exactly. See, you got this. You're thinking, Clayton, this is probably too easy. So once we're done all the, basically the formula at the top, we're going to have just a single scalar number. And if we look at the bottom, all we're doing is we're taking the norm of that vector, dx, which is 1, 1, 1, and we're squaring it. And we know that the norm gives us another scalar. So once we throw everything into the equation, we're going to have a scalar divided by a scalar. So our result for the strain in that direction, it's just going to be a number. It's not going to be a matrix. It's not going to be a vector. It's just going to be a number. So my question for you, because this is one of the harder ones, how are you feeling about part B? I gave you dx, I gave you E small. Can you find the strain along dx? You think it's pretty doable? Yeah, looks good. Wonderful. Let's go on to the next question. This one is going to be the trickiest. So what basically happens is we're looking at the change in angle between two vectors. Now, this is hard because students kind of have trouble visualizing what's going on. So let's say I take a plate and I'm compressing it, doing whatever. I'm going to deform it. Now, if I had two vectors inside of the plate, as you can kind of see in the webcam, after I deform the plate, those two vectors, of course, are going to either get squished or maybe they're going to get pulled further apart. But basically, the angle between these two vectors, once I start deforming my plate, it's going to change. The whole part of question C here is saying, all right, how much did it change? What is the angle by which it changed? Now, if we look at the lecture notes, we didn't actually derive this formula because it is really long and gross and pretty greasy. So I just gave it to you guys. So if I ever ask for the change in angle between two vectors after deformation, we're always going to this formula right here. Now, the right-hand side of the formula, if we look at it, it's almost identical to the formula we had on the previous slide. The only difference is instead of having dx everywhere, we now have dx and dy. So if we look at that right-hand side, we have dx, dy, and the small strain tensor. Three things. What's nice is we already know what the small strain tensor is. We know dx because that was from the previous question. And the only thing that we don't know is dy. But if we actually look at part C, I gave you what dy is. So on the right-hand side over here, we know absolutely everything. So we can go dx dotted with e small dy, that'll give us a scalar, and then we divide it by the norm of dx multiplied by the norm of dy. Again, going to be another scalar. So the right-hand side, that's not really a problem. What becomes a problem for students when they see this question is the left-hand side. Do we know what our final angle between our vectors are? What do you think? After I deform my two vectors, do I know the angle between them? I do? What is it? That's kind of a trick. We don't know the angle after deformation. And if we look at this formula, we need two things. Not only do we need the angle after deformation, we need the angle before deformation. So there's two angles on the left-hand side, and right now, we don't know either. All the question gave us was dx, dy, and e small. So it seems like we have one equation, but two unknowns. Now, here's what we use this formula for. Here's the secret. This formula is always for finding the angle after deformation. All right, so this will always be to find theta f. So then you say, all right, Clayton, if it's always for theta f, how do I know the initial angle, theta I? Well, take strain, throw it aside, and just think linear algebra for 2 seconds. If I were to give you just two random vectors, two of them, could you find the angle between two random vectors? What do you think? Yes, exactly. So you already know what dx is, and you know what dy is, where they were given to you in the question. So we know that through dot product, we can actually figure out what our initial angle is. Once we have our initial angle, we can come back to this formula and find our final angle. So if you may be wondering, what exactly is that dot product relationship? Well, it's this. dx dotted with dy is equal to the norm of dx multiplied by the norm of dy times cosine theta I. If we look here, dx, dy, we know what those are. They were given to us in the question. Our only unknown is going to be theta I, which we can solve for. And this is great because once we have theta I, we can then go back to the formula on the other slide and figure out what theta f is. So at this point, I know theta I and I know theta f. But here's the last trick to the question. The question's not asking you what theta f is. It's not asking you what theta I is. It's asking you for the change between the two. So what the question wants us to do is to take theta f and subtract it from our initial, or subtract our initial from our final. Basically, we just want the change in angle. We don't want the angle it ends up being. We just want the change in the two angles. So what do you think? Is C going to give you problems, or C also looking pretty good? This is the hardest question in the assignment. It's doable. Wonderful. That's what I like to hear. Perfect. Because again, hardest question. If we go to part D, it's asking for a matrix Q that transforms our small strain tensor into a diagonal tensor. So basically, if we look at that formula, it wants us to go Q times our small strain tensor times Q transpose, such that E small prime is just a diagonal matrix of the eigenvalues. And as we said a lot in our linear algebra portion, the matrix that does this for a symmetric matrix is a matrix that consists of the eigenvectors. So if we look at Q, the first row is P1, P2, P3. That is the first eigenvector of our strain tensor. If we look at the second row, Q1, Q2, Q3, that is the second eigenvector. So once you find the three eigenvectors, all you have to do is substitute them in. Now, there's one thing that caused students some trouble in the last assignment, and that was this. When you get eigenvectors in Mathematica, they're not normalized, because eigenvectors, the idea of them, they're just a direction. It doesn't matter if they're normalized. But once we substitute them into Q, if Q is what we're interested in, our eigenvectors have to be normalized. So here's the trick. Q is an orthogonal matrix, so once you get your eigenvectors in Mathematica, you have to normalize them before we put them into Q. The reason why is because an orthogonal matrix has a determinant, or a rotational orthogonal matrix has a determinant of 1. If the eigenvectors are not normalized, the determinant will not be equal to 1. So we have to normalize them to make sure a determinant is equal to 1. So again, all you have to do for this question, find the eigenvectors, normalize them, and then throw them into Q. Is there any questions about this, or is that also not too bad? No questions? Wonderful, wonderful, perfect. Let's go on to question 3. Now, I'm going to warn you, it's going to look pretty bad, so don't get too scared, because it's at the end of the day, this will be maybe 6 lines in Mathematica. Looks bad, but again, 6 lines in Mathematica. So it says, consider the plate in the figure below. So I didn't personally put the plate in, but there's a picture of a plate. And it says the displacement function of the plate is described by, and it gives us U1 and U2. So again, U's, U1, U2, and if U3, if applicable, those are our displacement functions. And basically, we want a lot of things with this question. The first one is determine the position function x. So when we're describing motion, there's 2 different ways. Displacement functions u, or position functions x. And there's a nice relationship between the two, so that's not going to be too bad. The next thing the question wants is a lot of different components. So if we look at A, B, C, and D, I guess technically B, C, D, E, whatever, they basically want the small strain and green strain components. That's it. So if I know my small strain tensor and I know my green strain tensor, I can answer everything in all 4 of these questions. So far, the only thing we need are position functions, small strain tensor, green strain tensor. That's it. And if we look at the last 2 questions, it says it wants a vector plot of our displacement function and a contour plot of our small strain tensors. Now, the reason why I want these plots is this. Once we're finding our displacement gradient, that's what we use to find our strain tensor, our displacement gradient. That's that ugly matrix full of all the partial derivatives. And most of the time, we kept it quite simple. We always had linear functions. So if I had a linear function and I took the derivative, it became just a constant number. If we look at these functions right here, question for you, are these going to be linear functions? Or are these right now, are they linear functions? What do you think? Are these are these right now linear functions? No, they are not. Another trick question. The reason why they're not linear functions is linear functions will always just have x1 or x2, and that's it. If we look at the questions, there's a couple things that give it away. The first one is we have x1 and x2 squared kind of sprinkled through. And we have certain scenarios where we have x1, x2, them multiplied together. So what happens is if I were to take the derivative of x1 squared, well, I'm going to get 2x1. So x always remains even after I take the derivatives. So what this basically means to us is that our strain throughout the plate, it's going to change depending on which location we're interested in. For instance, the corners might have more strain than the center. So this is why I want the plot of it. The plot of this plate after we do the strain tensors is basically showing us the distribution of strain throughout the entire plate, which is kind of cool to see. It's nice and colorful. You can figure out a lot of very nice things from it. So we're going to talk about how to do those things. The first one was the position functions. And we said that position functions and displacement functions are related very nicely, because here's the formula. My position function x is equal to big X, which is our initial point, plus u, which is our displacement functions. So if we look here, the only unknown that we really have is that big X. We know what u is. We were given u in the question. So if we were to expand this in vector form, x1 and x2, the two position functions that I want, are going to be u1 and u2, which we're given, plus big X1, big X2. The only trick is always remembering that big X1 and big X2, it's always going to be the same. They're not a variable that you substitute into. It's always just big X1, big X2. So for part A, where it wants the two position functions, all you have to do is add a big X1 to u1 and then add a big X2 to u2. That's it. It's actually very nice and simple. It almost looks too simple that you become really sus about it, but it's actually as simple as it looks. Now, moving on to the next part, we said that we can answer all of the questions if we know our two strain tensors, our small strain tensor and our green strain tensor. Well, what are the formulas for them? Our small strain tensor is 1/2 of nabla u plus nabla u transpose, and our green strain tensor is 1/2 of nabla u plus nabla u transpose plus nabla u transpose multiplied by nabla u. Now I'm going to ask you another question. Looking at these two strain tensors and their formulas, what's the only unknown variable that we need to solve for in order to determine these two small strain tensors? What's the only variable? What do you think? The u, exactly. So once we know what nabla u is, we have the entire question basically answered, because all we need is that displacement gradient. How do we find that? Well, in 3 dimensions, this is the formula, but since we're in 2 dimensions, our formula is going to simplify. It's just basically the partial derivatives of u1 and u2 with respect to big X1 and big X2. So we can find those partial derivatives, and then we can carry on and find our strain tensors. So for E small, it's going to look something like this. It's doable, but the key here is it's pretty ugly, as we can see. And this is the nicer of the two. If we go on to the green strain tensor, which is this formula right here, we're going to get this. Don't ever solve this by hand. This will take you way too long. It gets really gross, as we can see. So what we're going to do is we're just going to look at how to do it in Mathematica. So here's the code that's going to basically get you through the entire assignment. We're going to define u as a vector u1 and u2. Now u1 and u2 you will define before you do this. It's given to you right in the question, so you can just define it. After that, we're going to define the vector big X, which is going to be big X1, big X2, always. Once we have these two defined, we can calculate that displacement gradient, that thing with all the partial derivatives, by using the table function. So I can say that grad u, that's my own personal way of saying the gradient of u, is equal to, and then I go table, and then basically I take the derivative of u with respect to big X. That's all I do. So if you just copy and paste this code directly, this will give you your displacement gradient. Nice and simple. Because we said that once we have that displacement gradient, we can find our strain tensors. So in Mathematica, if I want to find the small strain tensor, I'm just going to use this code, 0.5 multiplied by the gradient of u plus the transpose of the gradient of u. The trick comes in with the green strain tensor. The formula is the same, but at the end of the green strain tensor, we have matrix multiplication. So what we have to do is we have to make sure that if we're doing matrix multiplication in Mathematica, we have to put a period instead of a star. But basically, if you just copy those 5 lines of code, u, x, gradient of u, e small, and e green, you have the entire question answered. The only thing that's actually required of you is just defining what u1 and u2 are, which you're given in the question. So you just have to basically copy and paste. Now the nice thing is once you run the code, you have your 2 tensors. But if we look at the question, it doesn't ask you for the entire tensor. It wants specific components, mainly that 1, 1 component, the one on the top left. So what we can do in Mathematica is we can actually call specific components. So if I wanted to call the component as a variable, and I define my green strain tensor as e green, I would just go double square brackets 1, 1. This will give me that component in terms of x1 and x2. So again, the key here that we said is all of our strain tensor components are going to be a function of x1 and x2. So if I were to call it just like this, it's going to give me x1 and x2 in the formula. So that's what you're going to want to do for the first 2 parts. The second 2 parts said it wants the components again, but it doesn't want them in terms of x1 and x2. It wants them at specific locations. So if I know what x1 and x2 are, I can substitute them in to figure out what exactly the component will be as a single number. How do we do this in Mathematica? All we have to do is go the same thing as before. If I'm interested in the component 1, 1, I would go e green, double square brackets 1, 1, and then I would add this piece of code. So I'm going to bring my mouse onto the screen so you can see, and all I have to do at the end to substitute my variables in is this right here. Now this part right here, this slash period, this is almost the equivalent of saying when, okay? When. What I'm saying to Mathematica is I'm saying I want this component 1, 1 when x1 is equal to 2 and x2 is equal to 4. That's all we're doing. So you're going to find your component, you're going to say when, and then you're going to specify the values of x1 and x2. The question says it wants them at the centroid of the plate. So if you look at your figure, you can figure out where the centroid is. You have x1 and x2, you just need to substitute it in. So this right here would call the components of e green 1, 1 when x1 is equal to 2 and x2 is equal to 4. So is there any questions about this? This is the majority of the question. How are you feeling? Hopefully pretty good?
Yeah, good. Thank you.
Perfect, perfect. All right, awesome. So going to the next little part, this is the last part, and I'm just going to skip ahead really quick because all you need to do is use 2 predefined functions in Mathematica. It says it wants a vector plot and it wants a contour plot. The nicest thing for us is vector plot and contour plot, the name is the function. So for vector plot, all I need to do is go vector plot, type in what function I want. In this case, let's say it's the first component of e small, and then I just have to define the horizontal and the vertical directions of the plot. So for instance, if my plate goes from x1 from equals 0 to 2, this is what I would put in. If my plate vertically goes from x2 equals 0 to x2 equals 2, this is what I would put in. And it's going to be the same thing down here. Once you run this, you basically are going to be given your plate as a square, and it's going to be a colorful distribution inside showing you where the maximum strain is, where the minimum strain, all that kind of fun stuff is. So it's actually quite nice because it makes me at least feel really smart once I get one of those big distributions all over the place. So that's going to be it for question number 3. So in general, is there any questions about number 3 or pretty good? No? Good. Wonderful. So we're going to go to the last question. This is the last one for marks. There's question number 5, but it's a bonus question. This is the last one for marks, and it is quite simple. When we talked about stress this week, we said that stress basically comes down to 3 formulas. You got one for a traction vector, you got one for the normal stress, and then you got one for the shear stress. And that's all there really is to stress, so it's going to be nice and simple. Question 4 says that the Cauchy stress at a point in a continuum is given by, and we have a nice matrix. And it wants us to determine basically 4 different things. The first one is the traction vector on the plane passing through the point and defined by the equation 5x1 plus x2 equals c. The second thing is the angle between the traction vector and normal to the plane. And then finally, part C says the normal and shear stress components acting on the plane. So if we remember those formulas, I don't expect you to memorize them, but if we think about them, they always had one thing that was kind of constant throughout, and that was our normal vector n. In order to find all of these things, we need to find what this normal vector is. And the only kind of piece of information we're given in this question is this plane equation 5x1 plus x2 equals c. So I don't expect you to know this because it's kind of outside the scope of this course. But if this was our equation for the plane, what do you think our normal vector is? What do you think?
Could you repeat the question?
Yeah, no problem at all. We need a normal vector n, so it's going to have 3 components. If I were to give you this equation for the plane that it acts on, perpendicular to, what do you think our vector is if this was our equation? It's kind of a tricky question, but it's nice and simple once you know. Yes, exactly. Sorry, I didn't see chat. Exactly. 5, 1, 0. Exactly. So that's going to be the only trick you need to know for this question. After that, you're absolutely fine. There's one, I guess, smaller trick later, but we're going to discuss it. So now that you know that, you have your stress tensor, and as you just said, you have your normal vector. You got both of them. If I want the traction vector, all I'm doing is I'm taking my stress tensor, which we're given, and multiplying it by that normal vector. Now here's the second part of this question that you have to remember. This is going to be the key. The normal vector, when we're dealing with stress, it always has to be normalized. Always. It's solely to define a direction. It's not an actual vector. It's a unit vector. So that vector that you said 5, 1, 0, that is correct for the direction. But before you throw that into this formula, you have to normalize it. Okay, so that's kind of the second trick. You find 5, 1, 0, and then you normalize it. After that, you're good to go. You can take n after it's normalized, and you just throw it into this equation. You have your traction vector. If you want your normal stress component, well, all you're going to do is take your traction vector, which you solved for above, and then you dot it with the normal vector. That's it. And then finally, for the shear stress, you take your traction vector, and then you subtract the normal stress multiplied by that normal vector, and then take the norm. So if we were to look at the top one, we're taking a matrix and multiplying it by a vector. What do you think the result will be? A scalar or a vector? If we take, it's actually going to be a vector. So basically, here's what's happening in our diagram. When we take a matrix and multiply it by a vector, we are going to get a vector. And what this is this is the vector of all the stresses acting on this plane through this point. Now what we do with that vector is we can split it into components. What we want is we want a component of that vector acting normal to the plane, and then we want a component of this vector acting parallel to the plane. So after we take our vector here, we can dot it. When we do a dot product, the result is a scalar. So this will be basically this will be a scalar, and then the shear stress will also be a scalar. It's kind of like thinking this. Think of this right here going down the plane as our x-axis, and then in the direction of the normal vector, this is our y-axis. If I were to give you this vector in that plane, saying Tn, it's almost the equivalent of saying what is the x component and what is the y component. In this case, our x component is our shear stress tau, and our y component is our normal stress sigma. Does that make sense? I'm hoping that it does. Yes? Wonderful. Perfect. So that's it for question number 4. I'm going to go back because there's one last thing, and that is part B, where it says the angle between the traction vector and normal to the plane. Well, there's no real trick to this. You have the traction vector as a vector. You have the normal vector as a vector. If we have two vectors, we can find the angle using the dot product formula. So for that question, just the dot product formula. There's nothing special. I know it looks like there's supposed to be a trick. There's not. You just have to use the dot product formula. All right. So last question, which is the bonus question. And it's a lot of word garbage, but it's actually not too bad once you substitute everything in. So if we look at the question, it says if sigma 11 is 1 MPa and sigma 22 is negative 1 MPa, while all other stress components, sigma ij, is equal to 0, at a point on a continuum, prove that the only plane on which the traction vector is 0 is the plane with the normal vector in the E3 direction. Now, again, it looks like a lot of words. It doesn't look like we're given a lot. But let's just take a look at it. Are we given our stress tensor? What do you think? Are we given our stress tensor indirectly? What do you think? Are we given? Yes, we are. If we were to look at our stress tensor, it says that sigma 11 is 1. Sigma 22 is negative 1, and everything else is equal to 0. So even though it doesn't look like it, we're actually given the entire stress tensor. The question says it also wants us to investigate the case where our traction vector is equal to 0. So we also know that our traction vector is just going to be 0, 0, 0. So we're actually given a lot of information. Now what's nice for us is we know that there's a very nice relationship between the stress tensor and our traction vector. That is this. Our traction vector is equal to sigma multiplied by n. So if I were to expand it out, we know that our traction vector is just a bunch of zeros, and our sigma is 1, negative 1, with everything else being 0. And the question says is prove that the normal vector in this case is aligned with the E3 axis. All right, it's aligned with the E3 axis. So if that's the case, and it's aligned with the E3 axis, what should N1 be? If our vector is going in the E3 direction, what should N1 be? Zero. Exactly. See, you got this. If it's going in the E3 direction, what should N2 be? N2. Nope. If it's if it's still going in the E3 direction, so it's like going only in the Z direction. If it's going only in the Z direction, is there going to be an X or a Y component? Yes, 0. So basically what this question wants is you to take this formula and prove that the only way this formula works is if N1 is equal to 0, N2 is equal to 0, and N3 has to be 1. Realistically, N3 can be anything because, again, it's just going in the E3 direction. But remember that for these normal vectors N, it has to be normalized. So therefore, we would say N3 is technically 1, even though you can prove that it can be any scalar. 0, 0, and any scalar. And that's all the question wants you to do. For what values of n does this statement hold true? So you can just try playing around with it. As you can see, once you get your 3 equations, because that's essentially what we have, it becomes pretty obvious. Yeah. All right, so what do you think? That's it for this week's assignment. You feeling pretty good, pretty confident? Yeah, looks good. Wonderful, wonderful. So we're approaching the end of our time. We still got 5 minutes. If you have any questions, just let me know. I'm happy to answer them. If not, have a great long weekend. I know that you guys could really use the long weekend, so I hope you can take the time and just relax for a bit. You guys deserve it after all the hard work you guys have put in. Is all of 398 just linear algebra? Yes. Yes, and the reason why is because are you taking 372 right now? Or have you taken 372? So what happens is, in our building, you've talked about degrees of freedom, right? Degrees of freedom. What happens is all those degrees of freedom can actually be translated into a matrix. And that's how we solve for the displacements. It sounds really bad, but all of structural analysis is linear algebra. Yeah, unfortunately. Yeah, so much fun. I know when I first saw it, I was completely overwhelmed, and I'm going to be honest, I'm still sometimes completely overwhelmed, especially when Yong's talking. But yeah, you'll see that all of structural analysis is linear algebra at the end. Yeah, so much fun. Yep, no problem at all. Again, I hope that you have a wonderful weekend, and just message me if you have any questions. Always happy to help. And thank you for showing up. Would have been awkward talking to myself. Perfect. See you later.